The only thing that would change would be this value of n. So this is some fundamental quantity that's gonna be multiplied by some integer. So let's figure out what this, calculate this actual fundamental quantity. So 4 pi, so that fundamental quantity I'll just label as a sub 0 times 8.85 times 10 to the negative 12th times h bar squared, that's 6.626 times 10 to the negative 34th over 2 pi squared. And let me just double check that, or actually, we did that yesterday. There was 6.626, blah, 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 negative 30, okay. Divided by mass of the electron. One off of memory on that one. Negative 31st times the charge of an electron, 1.6 times 10 to the negative 19th squared. Someone be kind enough?
Is it negative 34?
Yes. And we were about to find out whether I made Carol's error in values there.
.303 times 10 to the negative 73.
That, no.
I got 2.09 times 10 to the negative 9. I beat you.
I don't know if that's right either. But 10 to the negative 73 would have that, these are radii, that would put it orbiting inside the, all the electrons inside the nucleus.
I changed. I got 5.03 times 10 to the negative 11.
5.03 times 10 to the negative 11th?
Yeah. Or 5.303.
I got 3.33 times 10 to the negative 10.
We are cruising right along here.
Hurry up, yeah.
Some would claim that there is a universe in which each of those would be correct.
Can I write that on my test?
Yeah, there would be a universe where you would have every answer correct, and a universe where they're all completely wrong.
Word.
Which one are we in?
I forgot which universe I'm in, I'm sorry. Forgot it was Tuesday.
Somewhere I've got Yep. Okay, looking at my notes. Do we have confirmation of any of these?
I'm doing it.
What'd you get? Oh, you're doing it now.
I got the 5.303.
So we have 2 votes for that one.
So did I.
Hey, he was the one who mentioned it. Hey, he can't vote twice.
No, Jack's the one who said that one earlier, right?
Yeah.
But that's the one that you said earlier.
That was
Ethan had that one. That was, Jack had said that one. That's why I
I
crossed
got
it out.
5.3. I got 5.303.
Okay.
Okay, I'm off.
All right. However, I would take points off you actually put that down on the test and left it like that, what are we missing?
Units.
All right, that part we remember. What are the units?
The acceleration.
No.
What is the A sub naught? What do we find?
That's, A sub naught is this bit right here.
Radius. Is that R?
You're right, it's radius.
So it's meters.
Yeah, it's meters.
Those close.
Angular meters.
Angular meters has not been accepted by the worldwide community yet, unless angular meters is an angle. So you're ahead of your time or you're completely out of time, so what to do. All right, this value right here is known as the Bohr radius. And so Bohr's making the claim that the orbital radius of an electron is going to be some multiple of this based on n squared, so it's either going to be that, or it's going to be 4 times that, or 9 times that, or 16 times that. So everyone in here has had chemistry? Do you remember quantum numbers? Shells? All right. The n would when n is 1, that's the first shell, n is 2, that's the second shell. This is the first quantum number.
I never heard it called a quantum number.
What'd you hear it called?
Well, just shell number.
Oh. It's the first quantum number.
Can you have half a quantum number?
Not at that level. You can have halves at the second or third one.
Like 2.5 or 3.5?
Yeah.
But not 0.5.
You can have 0.5 also. Again, not at this. N is going to be one of the counting numbers. But there are 4 quantum numbers. And the whole Pauli's exclusion principle is that no 2 electrons can have the same set of quantum numbers for an atom. They will not exist in the exact same space. There's got to be some difference between them. All right, so what we have here is now this idea that electrons can't just be anywhere orbiting the nucleus, they have to be at certain levels. Now, if it does change levels, because electrons can change levels, the way we know of it now, if it gets hit by a photon, has enough energy, it can jump up to the next higher level. It's not stable there, so at some point it's going to come back down, and when it comes back down, it loses energy. So, how much energy is it going to lose? Well, let's take this and take a look at the energy of an electron orbiting a nucleus. We're not worrying about the electron bursting into flames. Not quite sure what that would look like. But I'm sure there's some AI programs out there where if you typed in electron bursting into flames, it would show you a picture. So what are the 2 types of energy that we care about here?
Kinetic.
All right, got half of it down.
Potential?
There we go. I'm about to ask that question. Let's see who actually remembers. What's the formula for kinetic energy? Not quite the unison I said before, or the enthusiasm. However, enough of you remember, so thank you. There's hope for 30 years from now when I ask. Plus, what is the potential energy of a charged particle?
MGH.
Yeah. This is a Physics 152 question.
KQ1, Q2 over R? Or maybe, wait, no, it's just 1Q. I don't know.
Can you ask the question one more time?
The formula for potential energy All right, so in general, what's the formula for potential energy?
MGH.
Let's see. Which one?
Thank
Oh,
you.
which one?
Thank you.
Oh.
All right, the one associated with this conservative force, the one that I had written over here, the one associated with this conservative force, the electric force. Remember, every conservative force has its own potential energy formula.
Oh. K Q1 Q2 over R.
Yes, you were correct. Then you questioned yourself. Close. So K, or 1 over 4 pi epsilon naught. Q1, Q2 over R.
Oh, is there a constant too? Like, let's see.
Say it
Is
again?
there a constant too? They have to add, like, let's see.
Oh, plus C. We're not worried about that because what we're ultimately, yes, yeah, there is plus some constant, but ultimately, I can set potential energy 0 equal to anywhere I want. And so let's go ahead and set U equals 0 at R equals infinity. And we'll drive that to 0. Also, what I'm really ultimately concerned with is the change in energy, so C's gonna cancel out. All right, so I've got this right here, the charge we're dealing with electron rotating, going around a proton, in other words, a hydrogen atom. So the charge, one of the charges is E, the other charge is negative E. I do care about the negative sign here. We're dealing with a scalar, the negative is not telling me a direction. Whereas before we already took direction into account. So I got 1/2 mv squared minus 1 over 4 pi epsilon sub naught times E squared over R. And that equals the total energy. Well, we can take it one step further because we have a formula for V, which was on the previous page. Let's see, is that the form I want, or do I want the other form? I want that form over there. Yeah. So that is equal to 1/2 m times, well, actually, I have mv squared right there already. It's just gonna be 1/2 times 1 over 4 pi epsilon sub naught times E squared over R minus 1 over 4 pi epsilon sub naught E squared over R. This right here is a substitution for mv squared right there. Mv squared is equal to this plugged in. Ultimately, the base here is the same, I just have a 1/2 in front of that and a 1 and negative 1 in front of that. So we end up with a total energy of negative 1 over 4 pi epsilon sub naught E squared over R. So the total energy is negative given the way I've defined potential energy. And that's typical for things that orbit. We can do it with satellites going around the Earth and we'd end up with something similar, except it'd be negative big G, mass 1, mass 2 over R. Questions up to here?
Is that just for a perfect circle?
Yes, we are assuming a perfect circle. That assumption came into account at this point right here.
When we had R.
When we assumed it's all centripetal acceleration, so v squared over r, we didn't have another tangential component.
So, I don't know if this is a too in-depth question, but if Earth, I don't know if Earth is a perfect circle,
It's not, but.
do they make the orbit a perfect circle? Do they use that equation for satellites and stuff?
It depends on how much money you want to lose. At this level, you generally consider orbits to be perfect circles. However, in reality, all orbits are elliptical, at least on the macro scale, they're all elliptical. And so there's equations that you can do to deal with that. Electron orbits become far more complicated than what we're presenting right now. All right, so this is the total energy, but I do have a value for R. Because remember, from what we had a couple pages ago there, the actual orbital radius is going to be this Bohr radius times n squared. So let's plug that in. And I'm going to go ahead and start a new page there. So my energy is -1/2 not -1/2, man. Oh, I did lose a 2 there. Should be -1/2. -1/2, 1/4 pi epsilon sub naught e squared over r. So that is negative e squared over 8 pi epsilon sub naught times 1/r, which is 1/4 pi epsilon sub naught. That was h bar squared over, that's mass of the electron, and then E squared.
Is that an H bar or a K?
Oh, times n squared. That's h bar squared.
Okay.
And that's an n.
No, I just could not tell. I
Yeah,
just said
no,
H bar.
Dividing by a fraction, same as multiplying by the reciprocal. So this becomes negative e squared over 8 pi epsilon sub 0 times mass of the electron, e squared over 4 pi epsilon sub naught h bar squared, 1/n squared. We can simplify this. Negative mass of the electron, e to the 4th power, over 32 pi squared, epsilon sub naught squared, h bar squared, times 1/n squared. And a quick check, just to make sure I didn't make some careless error. Nope. Looking good. All right, let's do some calculation. Let's figure out what that is. Check out our calculator skills here, see if we come up with 3 choices again.
At this point, I shouldn't even try.
Well, despite what Yoda says, there is try.
There is.
All right, so that bit right there, we have a mass of the electron, 9.11 times 10 to the negative 31st kilograms, times the charge of an electron or proton, 1.6 times 10 to the negative 19th to the 4th power, divided by 32 pi squared times epsilon sub naught squared, so 8.85 times 10 to the negative 12th. That would be coulombs. This would be coulomb squared per Newton meter squared. And that's the whole thing is squared. Times h bar squared, 6.626 times 10 to the negative 34th. over 2 pi. And the units of Planck's constant are joule seconds. Why am I blanking? What did I write down yesterday? Nope, that's not it. Meter squared kilogram per second. And that is squared. All right.
I got 7.15 times 10 to the negative 54.
Word. You're at 2.17 times 10 to the negative 18.
That's also what I got.
You got the second one?
Yes.
I got 2 points.
So we got three people with that second value.
Keep them off this shit.
Do you have, might be that you didn't square one something?
Sorry?
Oh.
Oh, we speak the same language.
Then I got 6.78 times 10 to the negative 20. Also different.
No, we only have 2 different answers. Just eat
Okay, that's
yours
right,
every
that's
day.
it's mine there. It's gonna be one of those, I knew it wasn't to the negative 54th, the other ones, I have it in different units here, so, I think it is the 2.17. Fourth wave.
It is the 2.17.
I probably should write that down so that in the future